Introduction. From determining the cheapest way to make a hot dog to monitoring the working of a factory, there are many complex computational problems to be solved. Before executable code can be produced, computer scientists need to be able to design the algorithms that lie behind the code, be able to understand and describe such algorithms abstractly, and be confident that they work correctly and efficiently. These are the goals of computer scientists. A computer problem, a specification of a computational problem uses preconditions and postconditions to describe for each legal input instance that the computation might receive what the required output of actions are. This may be a function mapping each input instance to the required output. It may be an optimization problem that requires a solution to be outputted that is optimal from among huge set of possible solutions for the given input instance. It may also be an ongoing system or data structure that responds appropriately to a constant stream of input. Example, the sorting algorithm is defined as follows. Precondition, the input is a list of n values including possible repetitions. Postcondition, the output is a list of consisting of the same n values in non-decreasing order. An algorithm is a step-by-step procedure that, starting with an input instance, produces a suitable output. It is described at the level of detail and abstraction best suited to the human audience, who must understand it. In contrast, code is an implementation of an algorithm that can be executed by a computer. Pseudocode lies between these two. An abstract data type, computers use zeros and ones, ends and ors, ifs and gotos. This does not mean that we have to. The description of an algorithm may talk of abstract objects such as integers, reals, strings, sets, stocks, graphs, and trees. Abstract operations such as sort the list, pop the stock, or trace a path, and abstract relationships such as greater than, prefix, subset, connected, and child. To be useful, the nature of these objects and the effect of these operations need to be understood. However, in order to hide details that are tedious or irrelevant, the precise implementations of this data structure and algorithms do not need to be specified. For more on this, see Chapter 3. Correctness. An algorithm for the problem is correct if for every legal input instance, the required output is produced. Though a certain amount of logical thinking is required, the goal of this text is to teach how to think about, develop, and describe algorithms in such a way that their correctness is transparent. See Chapter 40 for the formal steps required to prove correctness. And Chapter 34 for a discussion of for all and exist statements that are essential for making formal statement. Running time. It is not enough for a computation to eventually get the correct answer. It must also do so using a reasonable amount of time and memory space. The running time of an algorithm is a function from the size of n of the input n instance to a given bound and the number of operations the computation must do. See Chapter 35. The algorithm is said to be feasible if this function is a polynomial, like time n equals to theta n squared, and is said to be infeasible if this function is exponential, like time n equals theta 2 raised to n. See chapters 36 and 37 for more on the asymptotics of functions. To be able to compute the running time, one needs to be able to add up the times taken in each iteration of a loop and to solve the recurrence relation defining the time of a recursive program. See chapter 38 for an understanding. and chapter 39 for an understanding of Tn equals etc. Meta algorithms. Most algorithms are best described as being either iterative or recursive. An iterative algorithm, which part 1 takes one step at a time, is ensuring that each step makes progress while maintaining the loop invariant. A recursive algorithm, part 2, breaks its instance into smaller instances, which it gets a friend to solve, and then combines their solutions into one of its own. Optimization problems, part 3. From an important class of computational problems, the key algorithms for them are following: greedy algorithms, keep grabbing the next object that looks best; recursive backtracking algorithm, chapter 23, try things and if they don't work, backtrack and try something else; dynamic programming, solves a chapter 24 solves a sequence of larger and larger instances, reusing the previously saved solutions for the smaller instances until a solution is obtained for the given instance. Reductions, use an algorithm for one problem to solve another. Randomized algorithms, flip coins to help them decide what actions to take. Finally, lower bounds, chapter 7, prove that there are no faster algorithms. Part 1, Iterative Algorithms and Loop Invariance. Part 1, Iterative Algorithms, Measures of Progress and Loop Invariance. Using an iterative algorithm to solve a computational problem is a bit like following a road, possibly long and difficult, from your start location to your destination. With each iteration, you have a method that takes you a single step closer. To ensure that you move forward, you need to have a measure of progress telling you how far you are either from your starting location or to your destination. You cannot expect to know exactly where the algorithm will go, and you need to expect some weaving and winding. On the other hand, you do not want to know how to handle every ditch and dead end in the world. A compromise between these two is to have a loop invariant which defines a road or region that you may not leave. As you travel, worry about one step at a time. You must know how to get onto the road from any start location. From every place along the road, you must know what actions you will take in order to step forward while not leaving the road. Finally, when sufficient progress has been made along the road, you must know how to exit and reach your destination. Hopefully, this happens in a reasonable amount of time. A paradigm shift, a sequence of actions versus a sequence of assertions. Understanding iterative algorithms requires understanding of the difference between a loop invariant, which is an assertion or picture of the computation at a particular point in time, and the actions that are required to maintain such a loop invariant. One of the first important paradigm shifts that programmers struggle to make is from viewing an algorithm as a sequence of actions to viewing it as a sequence of snapshots of the state of the computer. Programmers tend to fixate on the first view because code is a sequence of instructions for action and a computation is a sequence of action. Though this is an important view, there is another. Imagine stopping time at key points during the computation and taking still pictures of the state of the computer. Then a computation can equally be viewed as a sequence of such snapshots. Having two ways of viewing the same thing gives one both more tools to handle it and a deeper understanding of it. An example of viewing a computation as an alteration between assertions about the current state of the computation and blocks of actions that bring the state of the computation to the next state is shown here. The challenge of the sequence of actions view. Suppose one is designing a new algorithm or explaining an algorithm to a friend. If one is thinking of it as a sequence of actions, then one will likely start at the beginning. Do this, do that, do this. Shortly, one can get lost and not know where one is. To follow this, one needs to keep track of how the state of the computer changes with each new action. In order to know what action to take next, one needs to have a global plan of where the computation is to go. To make it worse, the computation has many ifs and loops, so one has to consider all the various paths and the computation may take. The advantages of the sequence of snapshot view. This new paradigm is a useful one from which one can think about, explain, or develop an algorithm. Pre and post conditions. Before one can consider an algorithm, one needs to carefully define the computational problem being solved by it. This is done with pre and post conditions by providing the initial picture or assertions about the input instance and a corresponding picture or assertion about required output. Proof of correctness of an algorithm. It is important that you know that your code works. The proof might be a formal mathematical one or it might be informal hand waving. Either way, the formal statement of what needs to be proved is as follows: pre-con encode to post condition. This states that if the input instance happens to meet the precondition and the code is executed, then in the end, the output will meet the post condition. On the other hand, if the precondition was not met, then except for being polite, there are no requirements on what your code does. Check each computation path. The computation from pre to post condition will follow one of possibly many paths. For each such path, you need to be confident that the post condition will be met in the end. Suppose that the above max A, B, C code had not two if then else statements but a sequence of R of them. There would then be two raised to R paths, though which the computation might follow. Checking each of these would be too much work. Instead, we will break the computation into sub-computations. One step at a time. A main theme of this book is to implore you not to think about the entire computation all at once. As recommended in Alcoholics Anonymous, worry about one step at a time. Start in the middle. Instead of starting with the first line code, an alternative way to design an algorithm is to jump into the middle of the computation and to draw a static picture or assertion about the state we would like the computation to be in at this time. This picture does not need to state the exact value of each variable. Instead, it gives general properties and relationships between the various data structures that are key to understanding the algorithm. If this assertion is sufficiently general, it will capture not just this one point during the computation but many similar points. Then it might become a part of a loop. Sequence of snapshots. Once one builds up a sequence of assertions in this way, one can see the entire path of the computation laid out before. 1. Fill in the actions. These assertions are just static snapshots of the computation with time stopped. No actions have been considered yet. The final step is to fill in actions code between consecutive assertions. One step at a time, each such block of action can be executed completely independently of the others. It is much easier to consider them one at a time than to worry about the entire computation at once. In fact, one can complete these blocks in any order one wants and modify one block without worrying about the effect on the others. Fly in from Mars. This is how you should fill the code between the ith and the I plus first assertions. Suppose you have just flown in from Mars and absolutely the only thing you know about the current state of your computation is the ith assertion holds. The computation might actually be in a state that is completely impossible to arrive at, given the algorithm that has been designed so far. It is allowing this that provides independence between these blocks of actions.